Hi, in this video we're going to show how to simulate a simple type of robot arm that moves in 2 dimensions. I've got a mechanical link here in yellow. This is about 2 feet long and weighs a kilogram. And I'm going to connect it to this mechanical anchor, just a fixture that can't be moved. That's sort of going to be the shoulder of the robot arm. First I make sure that these 2 pieces are attached strongly so that they'll be held together. So we make a joint. And then I'll put a DC electric motor here. We'll put a couple of volts on the motor over in the component properties panel on the right hand side of the screen. We'll set the gear ratio to 1 to 100 so that there will be plenty of torque to turn the arm. This is an electromechanical simulation, so we'll be simulating the motor and the constant voltage drive circuit as well, and we'll be able to see how much current it takes to move the arm. If anything obstructs the arm, this is a serious problem with electric motors, then you'll see a lot of extra current. Let's make the next segment of the arm. So you can really look at problems that are going to actually occur. For example, if you use a mechanical linkage to push an air pump and something blocks the air and the air pressure builds up, the motor stops turning, you're going to get a lot of current and can burn out the motor. If you've ever had this experience with a vacuum cleaner, you know what I mean. And you can see it all in this simulation. So this is, real scientific simulation here. Engineering simulation. Alright. We've built the second joint. Let's attach the second motor to the system. We'll use just the same setup as the first motor, only with a negative voltage, so that it'll turn in the opposite direction, and you'll see why. The gear ratio of 1 to 100. Again, if we don't use a low gear ratio, the motor has trouble accelerating these arms as fast as it wants to turn them. Then we'll have problems. We'll have high current in the motor. You'll use up a lot of battery power and possibly burn out the motor if you've got plenty of battery power. We can simulate the battery, how many milliamp hours are in your battery. Anything we don't already have, we can make new components with back-of-the-envelope equations and pop them in there very quickly. Doesn't have to be mechanical, doesn't have to be electrical. If there are simple equations, we can do it. Let's see, I haven't set up the motor voltages quite right. I'll draw an approximately straight vertical line if the ratio of motor voltages is 2 to 1. Aha. But I had -5 to 2 instead of -5 to 2.5. There we go. So, and this is what simulation is for. If you make a mistake, you can catch it. There we go. Let me show something to hopefully give some confidence that this is real. I'm going to suddenly put gravity. So far the motor's been moving horizontal. These are used in pick and place machines, and they tend to move horizontally. But let me select all the massy parts here and put a force of gravity towards the bottom of the screen. So now we've put the acceleration of gravity on those parts. Now the arm is maybe attached to the corner of a table like a desk lamp or something, and is sticking up into the air. It's going to try to draw this same vertical line, but I haven't done anything in my controller to account for the force of gravity. And these are 2-pound links here. So it's not going to behave the same way. You can see stress at the joints. The separated dots show that there's some strain bending the joints that I gave. Of course, you could tighten the joints to make that look better. The question is, how strong are your real materials? And it's nice to be able to know. So it behaves very differently under gravity, which I hope gives some validation that we're telling you the truth here. Let me plot the motor current to show that you can get your your data out here that you need to do engineering. Find the first motor down at the bottom, and it's actually being driven at a negative current. So this second motor now is actually operating as a generator. I haven't looked at this plot before. In this case with gravity. So what we're doing is we're actually producing a whole bunch of energy by yanking on the axle of this bottom motor with this 4.5 pounds of weight. If I take away the gravity, we'll see a kind of a pulse of current to get the motor started, and then the current goes to a really low level once you stop accelerating something. It doesn't take much energy to just keep something moving unless there's a lot of friction. Let's turn the gravity back off and plot that quickly, in case anyone's still listening. I need the massy parts. I'm going to turn off the acceleration due to gravity. We'll run again. Okay, that's run. Now we're back. It's moving horizontally instead of downward in gravity. And now we're not getting any free energy by dropping these heavy parts. So we should see the motor current be positive instead of negative, which will mean that we're consuming energy. Here's the motor current, mostly positive. The whole structure oscillates a bit, which you can kind of imagine if you built this and twanged on it. It is going to shake, and that's affects the motor current. That's how it is. But you just see a small amount of current and almost all dissipated. So we have to pay to drag this thing across the tabletop, and maybe draw a line with that red magic marker. This is not operating as a generator now. But of course, motors work both ways. All right, thanks for watching.